All right, everyone. Thank you for joining us once again on Did You Know, the ESCO HVAC show. We're so grateful that you're here with us. So, I'm actually on vacation this week. If the background looks a little bit different, so I'm hanging out in Branson, Missouri, just taking a little time off, but I cannot miss my opportunity to hang out with this community. So, let us know where you're joining in from. Ray, you seen you were out there putting messages in before we even started. Thank you, sir, for hanging out with us. We got Ty Brenneman. Ty, how are you?
Doing fantastic.
And where are you at?
We're in San Angelo, Texas.
Okay. And Adam Kimmel, how are you doing, my friend?
Doing well. I'm up here in Milwaukee, so it's 50 degrees still up here.
50. Oh my goodness. Ty was just telling me he had what, 98, did you say, Ty?
98 right now, yeah.
Oh my gosh. I mean, it was like in the 80s here with the 100% humidity, and we're like, send me back to the Midwest. Oh, Osvaldo, thanks for joining us. We're glad to have you here, and let us know where you're joining in from. Everyone that is a part of this community, we really are grateful to have you here. We're all going through transitions. We're starting to have a pretty significant international community because we're all seeing a variety of changes no matter where you are. And that's what we wanted to do, is to be able to spend time talking about a variety of different aspects of our transitions. Now, Adam, you are with Koura. Tell us a little bit about Koura.
Yeah, so I my 1 year anniversary was yesterday.
Yeah,
So
seen that.
yeah, just joined. So our kind of claim to fame is mine to market. So we have a fluorine mine that is in very near the geographical center of Mexico. So I had the pleasure of being there
Yeah.
to see this fluorine material coming straight out of the earth. It was incredible. We were a few hundred meters down underground. It was a little bit, okay, what if something happened?
Yeah.
No, it
Where's
was
the rescue crew here?
yeah, and they were everywhere. An incredible facility, incredibly talented people, and it's just, you hear a lot about, the chemical industry, and there's this kind of non-natural feel to it, but to see that fluorine coming out of the earth was really amazing, and it made me just proud to be part of it, and to kind of show, hey, fluorine really is critical, and it does such an important, many important jobs for us. And so Koura is part of Orbia, so we're about a just south of $10 billion global business,
Mhm.
and we've been doing refrigerants for many decades.
Right. So Adam and I first got together when we started looking at what is the future of refrigerants, right? I love talking about the past. I mean, how can we understand where the future is if we don't know where our past got us from, right? So when we start talking about our refrigerant transitions, hopefully you are all very aware that we're going through an HFC phase down, a pretty drastic HFC phase down at the moment. And so over the next 12 years, we're going to be phasing out all of the most popular and common refrigerants that we know today: 410A, 134A, 404, a whole variety of them. And so we have a lot of different refrigerants that are coming to the market, and we need to understand what that looks like. And so Adam and I got together and we started talking about refrigerants internationally, and a big picture started coming together for where we are here in the United States. And so let's dive a little bit into some of these conversations, Adam, and give people an understanding of kind of where we're going and what your role is in education for Koura.
For sure. So yeah, Adam Kimmel, as I mentioned, I've been with Koura for just over a year. I'm now the senior manager of business development, focusing on the Americas. So the U.S. is certainly an important piece of that, but I also have Canada and LATAM responsibility as well. And our division is Orbia Floor and Energy Materials, and it's principally refrigerants that I look after.
So if you don't know Adam already, so Adam he's this really cool mix. He's the kind of guy that Ty and I really love hanging out with. So Adam gets to see the boots on the ground like we do, but he's also a mechanical engineer and chemical engineer, right? Yeah, I know you don't boast about yourself, but you are, and you get to see both sides of that world. So you give us the opportunity to understand what refrigerants look like, but also how they respond in the equipment, because you were into designing heat exchangers, coils, and how refrigerants worked in these coils before you got to this point where you're now like almost dedicated to focusing on refrigerant training. Is that correct?
Yeah, exactly. And a lot of the same challenges we would hear in the heat exchanger world, because we would get specifications that wanted 100% effectiveness and zero pressure drop and all these ideal, Ty's laughing. This can't have all of it, right? So the
There's
question
the most
is,
perfect blend.
right, what's the most important one? What's the
Yeah.
next most? What are the trade-offs? And how can you get as close as possible for as cheap as possible? So
Okay.
that mentalities help me kind of from an optimization standpoint to teach, and help to educate people as far as what are the, because nothing's free, what is the cost of this requirement and that requirement? And,
Right.
as we're seeing regulations, what would this regulation cause the industry to then do?
Yeah, and a lot of the stigmas, a big part of why we're here too is to help break these stigmas and bring some awareness. Ty and I was just having a conversation before here about these stigmas about like things like 32 and 454B and what's going to be around and what's going to replace them. And we're like, all right, this is a great day to talk about this. All right,
It's a million
so
dollar question.
it is. All right, so let's talk about the agenda for today and give everyone an idea of what things we're going to cover because we're doing a lot of refrigerant conversations here, but this one's different.
Yeah. Well, I think the where this always is going to start as far as why the change is regulations.
Hmm.
Regulations is going to be the driver for most of this. We talked a little bit about the ideal refrigerant. How can we get as close to that? And what are the features and aspects of an ideal refrigerant that we're looking for? What about the development timeline? How long will it take to make these new ones? And part of our point of view about why a single molecule isn't usually going to be enough anymore, given all the constraints and requirements that we see. The next one is 1234ZE. There's just many options out there, and our point of view is the 1234ZE is absolutely critical, and so I'm going to help try to make the case for why you should agree with me about
Okay.
that. But its critical role in enabling non-TFA blends, that's really one of the main value props, in addition to extremely low GWP. We're investing a ton of R&D in there. Um, Lifecycle climate performance is another theme that's starting to become important as GWP continues to push downward.
Mhm.
What are the other factors that then become higher influencers of, if our goal is truly decarbonization, what's the driving factor if GWPs are near zero? So
Sure.
that's an interesting one. And then the future. So being careful not to promise or commit to anything. My and our view about what we see in the future in terms of mobile HVAC and some of the other segments.
Sure. Yeah, and we're going to spend some time talking about like TFA and non-TFA. A lot of people don't understand what that is, so I think this is a very important conversation to start talking about going forward.
Yeah.
Yeah. Okay. So, we know why we're here. We need to change, and we get a lot of questions. Is Ty, what's the most common question we get about the refrigerant transition?
Oh gosh, there's so many. Why is it happening? Is the new one gonna be? Is it gonna explode and kill everybody? Like those are the two most comments that I get.
Hmm. And is this a patent-related transition that we're actually seeing right now?
All some expire, so we need a new one that's covered for the next 20 years, that kind of thing. Yeah, it's I've heard a few of that too.
Yeah,
But
Ty gets a lot of those, and so we'll talk about some of that as well as we move forward, and just understanding that we are truly making a difference to our environment that we live in. Right. And it's not just our industry. Many industries are going through these transitions, and there are a lot of, I would say, heavy consequences. There are heavy considerations as we make these transitions and as we look for lower GWP refrigerants for our equipment. And we're going to be making a lot of transitions in a very, very short period of time. So it's extremely important to be aware of these. And that's why we're so grateful that you're joining us all today. And it's very important that we get our information firsthand. So every week we try to bring in top educators from our industry, just like Adam, a manufacturer of refrigerant internationally that is here to talk about these transitions. So grateful for you joining us, everyone. And say, let us know where you're joining from. Yeah, that's right. Low GWP. That's kind of the whole conversation of the day, isn't it, right now? Thanks for hopping in here, Jason. And you got a link too, Jason. If you want to join us, I'm more than welcome to hop up in here. So let's dive a little deeper today and get into what our industry is looking like and what it's going to look like going forward.
so one of the biggest competitors that we see as a manufacturer is the do nothing refrigerant solution. So we constantly are fighting. Can't we just leave it alone? Uh,
R22. Why can't I have
yeah,
R22 back?
let's throw it in the Wayback Machine back
Right.
there. But the story really is starting with global temperature rise. So the United Nations International Panel on Climate Change, IPCC,
Yep.
that's a heck of a lot easier,
Yeah, absolutely.
has started to have these meetings and commitments every so often, and that's what really started a lot of this. So what they've said is the world needs to cut emissions by 45% by 2030
Hmm.
and achieve net zero, which means we produce as much as we consume by 2050 to limit global temperature rise. and their target is 1.5 degrees C, which, when I first heard that, I'm like, well, that's not really going to do anything, is it? I mean, 1 degree, would you even notice 1 degree? But if you think about the entire Earth, the mass of Earth, 1.5 degrees Celsius is a ton of energy. So think of the energy that it would take to raise the entire mass of the Earth that
Right.
temperature. And that time scale actually starts pre-industrial, so the 1870s and 1880s through 2100. And that was the critical threshold as defined in, I think it was 2015, the Paris Agreement. And the bad news is that we're not on track right now. So
Yeah.
despite the fact that we need to be cutting, emissions are increasing by about 14% projected over the decade of the 2020s. So it's not going the right way. Um, our contribution, HFC refrigerant leakage, can contribute a half a degree of global temperature rise. So if 1.5 degrees C is our goal, if at our current rate, it'll be higher than that, but a half a degree of that is can be affected by refrigerants,
Just us.
right? So that's a very mission and purpose focused
Wow.
number for me. Like when I
Yeah.
get up and do this work every day, I mean, we're fighting that half degree.
Okay. And now that we start thinking about our younger generations of technicians, particularly when we start getting into our Gen Z and into our alphas, they really do want to make a change to the world around us. Right now, some of our older generations, like ours, our X's and older, we haven't witnessed the change that has happened in the last decade. So we have new generations of technicians that are very much focused about contributing to a better planet, right? Making efforts to make changes to our world. And so we're hoping to educate you. We're hoping as educators, we're all talking on the same platform and we're all understanding that we do have a opportunity to make a change and we have a responsibility
Mm.
to comply with that and to uh, embrace it. It's difficult. We're all going through this, but it's not the first transition we went through. This one is just very, very important. And the beauty of social media has made us able to have this discussion.
Yep, exactly. So I think this is the most technical one I have here.
Okay.
Don't hold me to that, but
All right.
it's unpacking a little bit about how this warming actually works and why these meetings and protocols keep coming up, and why does it seem like there's always a new refrigerant, and that try to answer that kind of question.
Yes.
So if you look at how warming of the earth happens, it's radiative forcing. That's really the potential. So you've got this incoming solar radiation that you see. It's kind of in small text at the top there, but it splits into three factions. There's energy that's absorbed at the surface, around 48%. 29% of it's reflected back into space, and the remaining part of it is absorbed in the atmosphere. And it's this atmospheric absorption that's the target of a lot of this.
Sure.
So in the 80s, chlorine, the CFCs were there, chlorofluorocarbons, but we needed to get rid of that because of the ozone. It was hurting the ozone and thinning it.
Yep.
And so the Montreal Protocol focused on that. And the reason for that is because ozone absorbs 97% of harmful UVB rays. So not having the ozone is not an acceptable outcome because of how critical that barrier is.
Yeah.
The problem then became HFCs were too stable. Industry did too good a job because these molecules didn't break up enough in the
Right.
atmosphere. So
They
what started to
stayed.
happen? They stayed, right. So over the course of over a decade of being in the atmosphere, the problem with HFCs is, there's CO2 and naturals that are out there. HFCs actually extend the range of radiation absorption spectrum wavelengths. So it's kind of a larger umbrella that's catching the heat coming back into the atmosphere. So it extends that spectrum of radiation. So again, I have there, it's more than 10 years to degrade in the atmosphere, which increases that forcing. And if you think of how forcing is related to the energy absorption, just think of it in that equation that I've got there. Warming is proportional to the absorbed over the reflected. Interesting to note, that 48 absorption at the surface, if you add that to the atmospheric absorption,
Right.
it's higher than reflected.
Okay.
So even if we didn't emit anything, the Earth is going to heat up. It's the rate of heat that we're trying to
Trying to control.
control and limit, right? So if you think of a heat transfer problem, I always go back to my early days of heat transfer. It's that driving potential, trying to minimize that to have a more gradual warm up than a more drastic one.
Yeah, absolutely. And Ray made a good point. Back in, I always call it our generation. When we're talking about 1980s, 1990s, when we were in school, everyone heard about the hole in the ozone layer, right? And so as we start researching that and understanding that chlorine was a primary candidate to that ozone depletion, we started phasing out the refrigerants that contained chlorine. And now that we've moved past that, we understand of the global warming potential and exactly what we're talking about here, that energy that is being stored, we understand that we now have the responsibility to harness that warming power of these fluorinated refrigerants. And so that is the whole reason for this HFC phase down. And so now we've got two things that are driving this. We keep talking about how we got the Kigali Amendment to the Montreal Protocol. So we have an international treaty, as well as now we have the phase down that is being brought through the AIM Act. So now we have an act of Congress signed off by a different president. So we have a international treaty by one president, we have an act of Congress by another president, and we are making this transition. Now, what's it going to look like? Thanks for joining us, Jason. I'm glad you're here.
Hey, everyone. How are we doing?
Doing good. Doing good. All right. So a very, very good slide, a very, very good conversation to add in the classroom is what is warming of our planet and discuss the energy absorbed and the energy reflected. Mr. Tom Tebby, we're glad you're joining us out there. Mr. Tom Tebby has seen all of these refrigerant transitions, these phase downs and phase outs, completely understands that it is part of our curriculum. It is our job to teach this as we're going forward. All right, so let me hop onto this next one here. If I get behind, just let me know if I need to go forward or backwards on any of these slides. So I'll be running them from this side today.
Yeah.
And
so this will be the driest one, but to the point of regulation,
right.
This is sort of the when will we feel the impact?
Right. When will it hurt?
Right, exactly. Well, yeah, other than yesterday, right?
Yeah.
But the highlights of the AIM Act: 30% CO2 phase downs happened a couple of months ago, 3 months ago, I guess now in January, and are happening again in 2029. So I think worth noting is that baseline, because you hear, all right, well, it's going to be reduced to 10, a 10% reduction in baseline happened at the beginning of this, and then a 30%. That baseline was set in the early part of the 2010s. So a 10% reduction was significant because the numbers were actually higher. They just measured it against the baseline. So that's something that many don't realize. And another one is all segments pull from the same pot, so to speak. So the 410A segment really dominates this, but it's one pie. So CO2Es are CO2Es, and all the segments are going to be affected by what the other segments do. So it's important for collaboration, understanding, and developing solutions as partners, not in silos.
Right. Some refrigerant manufacturers or some refrigerants will be affected more than others because this isn't like a buzz cut where we just chop the top off. It's like an account, like you said, CO. It's the credits are the credits, and some refrigerants that are high GWP will start to go away, that are HFCs before those that are lower GWP HFCs.
Exactly.
Based on the credits.
Yeah, and that's the intent, right? Is to target the highest cost. If you look at GWP as the cost, target the highest cost first and move down. So I think the intent makes sense. And then when you have EVs and heat pumps driving demand while the quota is reduced, that's going to further constrain things. So what we see is, between now and 2029, the next 30%, we see this as the critical development window. And so. as many have started their, finishing up development of 454B and 32, there's no time to exhale, unfortunately, because of how long it takes that qualification to happen. Yeah. So it's a matter of like that 2029 phase down needs to inspire urgency. It isn't 5 years from now. That's when we have to be done.
Yeah, that's the ending point. Right. That's why we have these conversations. I mean, people keep saying, well, why are you talking about things that are going to happen 5 years, 10 years? Because that is the deadlines. And there's a lot of potential that we're going to be at those points before those deadlines get here. We've got things like California. It's already been doing 404 bans and 410A bans so that they're trying to be more aggressive on that. You got New York that is saying that they're looking at a 10 GWP limit on new equipment.
So a GWP 20, right?
Yeah, exactly. So we're really struggling to get everyone aware, and we're grateful that everyone is joining us because these are conversations we have to have. We get the question all the time. Well, when did this begin? Well, it actually began a decade ago, and we really got serious about it in the last 5 years. We started our very first 10% reduction in 22. we added that 30% reduction. So we're now at a 40% reduction from baseline. So those high GWP refrigerants like R404 that has a GWP of what, 3,920 or something in that range.
Right on.
Well, so if we think about this, so Adam, as a chemical manufacturer, if I have this bucket of GWPs, right? And Jason always talks about this leveraging our GWP bucket. If I have a GWP allowance, and let's say it is 3,920, I look at it and I go, okay, I've got a HFO of 1 GWP and I got an HFC of 3,920. I can make 1 pound of 3,920, or I can make 3,920 pounds of the one. That is difficult for a manufacturer of refrigerant, because then you have to look at the manufacturer of manufacturer of refrigerants, because then you have to look at the manufacturer of equipment and go, well, what's that demand going to be?
Right. And that, well, we'll get into this, but that has been our design perspective, is to say, how can we make their lives as easy as possible while reducing this GWP? So the ability to drop in and utilize existing equipment is a critical pillar of our development.
Yes.
As we look into this. But yeah, that's important, because, we could make a lot of people really upset if we don't, if the compatibility is not there.
Exactly.
So you were talking about time flying and being in the future and such. That phase down is just one part of the act for the refrigerant side. There's also a phase out on the equipment side that's coming online very shortly. Yeah. The technology transition rule.
Oh yeah.
Which is really expediting things. So we get this question. I've had it with contractors in the last week. So when is R410A equipment going to go away? I said, well, you're almost there if you don't realize that. I mean, most manufacturers will be done manufacturing R410A, particularly residential light commercial systems, by the end of this year. So we're in a very, very short period of time of making this transition.
Yeah, I mean, I look at those, the phase down as kind of the wind in the sail, but the technology transition's the brick wall the car is speeding toward. Like, that's it.
Right.
So, yeah. So,
that's the cliff we're about to go over, right?
That's right. Delay at your own risk, right?
Right. So where are we right now? So we know that our most comfortable refrigerants are going away. What are we doing?
So the state of the art. So how do we leverage the benefit of HFCs, which is, it doesn't harm the ozone. It performs really well, efficiency, low flammability, low to no toxicity. I mean, all of these things, we want to maintain that. And basically, what we love about HFCs is that they're extremely stable. So they're very stable in operation. They're also very stable out of operation. So we need to, ideally, it would be infinitely stable in the equipment. And as soon as it leaks, degrade immediately.
Let's say if it leaks. Yeah.
If it leaks.
Exactly. I mean, and safe, handling practices and things are a big part of all of this. So it's, not to be ignored. It's not like, well, the GWP's low, just bent this stuff all over the place.
That's what we're hearing. Yeah. Wow, it's low GWP, just let it go.
Yeah.
No, they still have to be recovered.
Yes. Right. Exactly. So what we see with HFOs, I'm not seeing the.
I got it here. I'm going to slide it back over.
Okay. Yeah. No worries. So back to chemistry class.
Yes.
It's an HFO is really just an HFC with a double bond in it. It's called a hydrofluoroolefin. And you can see the that arrow pointing to the double bond is the critical differentiator. So what that does is it creates kind of this landing pad for atmospheric hydroxyl radicals. That OH negative, which is in the atmosphere, is electronegative, and it attacks that bond because it has some, there's space to do it. If you look at the right side of that molecule, see those 3 fluorines? They create kind of a local stability. They block the ability for those atmospheric hydroxyls to get in there. And so that's why it takes so much longer to degrade in the atmosphere. And when we say long versus short, I mean, you're talking days versus years. It's literally 13 days for olefins to, 134A is 13 years to degrade. So that little double bond makes a ton of difference.
Same atoms, just reformulated, synthetically bonded.
Yeah, exactly. And then the process to manufacture them is different, of course, but that nothing's free though, right? If our goal is less stability so that it degrades in the atmosphere, the trade-off becomes flammability, which is a measure of stability, right? The more flammable it is, that
true, sure.
One of the things I'll point out to the viewers is that if you look at the olefin there, it has hydrogen, fluorine, and carbon. And we work with those chemicals on the daily in HFC. So this is really just an HFC with a double bond.
Exactly. Yeah, it's like a super HFC. You know, it's
Sure.
as we learn, we improve, and we figure out how to get closer to the ideal state, right? And so yeah, I think I've covered many of the time scales, but this days versus years thing is important. And that's really where, if we can prevent this, some of that solar radiation can be reflected back. It doesn't get absorbed in the atmosphere. All goodness. So the more HFOs we can adopt, the better, at the expense of flammability.
So we're still using the same atoms. We're
Mhm.
creating different molecular bonds. So we still have hydrogen, fluorine, and carbon. With a HFC, traditional HFC refrigerants, because of the strength of their bonds, they stay in the atmosphere much, much longer. And now with the olefin bond that we're utilizing in the same hydrogen or the same hydrogen, fluorine, carbon combinations, we're just able to, once it is accidentally, not intentionally,
Air quotes.
Mhm.
once it enters into the atmosphere, it's now able to break down much, much faster.
Yeah, it gives us a safety net, right? I mean, if in the event handling practices aren't done 100%, whatever, then at least
Right.
there's a mechanism to get that molecule ripped apart.
But we would still have the reintroduction of particularly like the fluorines back into like ground concentrations, right? So just like Ty was saying, one of the things that we hear is, hey, it's a low GWP. What can I do with it, Ty?
I'm not going to say it.
Right, right. And so that is a no, right? It is not a natural like a hydrocarbon, a CO2. We're not in those states. We are talking about synthetically created chemicals that need to be captured and not released into the atmosphere.
There's the 608 requirement for it to be recovered. Yes, the
Absolutely.
the refrigerant regulations still apply to these refrigerants for selling, carrying, distributing, and
Leaks.
recovery. Yes, and for recovery.
Right. Okay. That's cool. I'm glad to know about how that hydroxyl attack happens. That's a really good explanation of that because I get that all the time. Well, how does it decompose? How does it break apart faster? Well, we know about the olefin bond, but what's happening to that bond?
Yeah, and I think the double bond, the olefin double bond thing is known. It's like, well, if it has that, that's better. But it is the atmospheric hydroxyls that do the work for us.
That do the actual damage, right? For deconstruction.
Mhm.
Okay.
So what is the ideal refrigerant? What if we could just let me go to the R&D lab and sit there for however long until I can come up
Right.
with something that'll give
Because
you.
no one's working on this, right? We're all just waiting for the next patent so everybody can make billions of dollars.
It's inspiring because it's an innovation opportunity. There's a real need. If we could solve this problem, I'd probably be retired real soon.
Exactly.
Problem is, again, it's trade-off. So I like this spider chart. It's from Global Spec. I always try to put sources on here so that
Yes.
nobody can assume I came up with this. But if you look at the outer edge, so that it's gray in the middle, and I guess the more filled out that bubble is, the better. So if you look at the top, low GWP. This one's comparing R290, which is propane,
Yep.
410 CO2, and then 1234 YF as a representation of the HFOs.
HFOs.
Yeah, so for low GWP, everything looks good of those four except 410. What about toxicity? You can see the opportunity there. That many of them are good, and there's some of, I think 410A goes back out there too. So the toxicity piece is probably the best of all.
410A has a very high RCL. Yeah.
Yeah, exactly. Compressor efficiency. That's really where you see CO2 start to fall off, especially at high ambient temperatures. I mean, these physical limitations of so-called natural refrigerants have existed since the beginning of time in this industry, and every time they're investigated, they continue to show up. CO2 is lousy at high ambient. The pressure's high. It's the same story. So you see that reflected here in the spider chart. Compressor capacity, same deal. This is where 1234 YF starts to fall off a little bit because of performance. YF tends to give up, I don't know, whatever it is, 5 to 10% in a direct system replacement of performance. So, to the idea of let's just go to a single molecule HFO,
Sure.
can't necessarily do that if you want to get performance parity. Compressor system and cost, there's CO2 again. With are there compressors, are there heat exchangers, what's the balance of plant components, and even YF starts to fall off of there. No glide, which, glide doesn't necessarily have to be a swear word, and I'll talk more about that.
Okay.
But you can see, the impact of that starts to become, a challenge for zeotropic blends. They're not reflected here, but that's well, then I guess 410. But that's also a concern. Heat transfer pressure drop from the heat exchanger days. There's YF, falling off a little bit. And then the flammability concern, as we know, the HFO is going to be a little bit more flammable, and of course propane is crazy flammable. That's its limitation. So there's the shopping list on the left. So if anybody has an idea, we'll pay for the patent rights and list you as an inventor. But low cost, easy to handle, easy to detect, easy to manufacture. These are table stakes that are just good supply principles. Self-lubricating or compatible with lubricants is important from a ease of use standpoint, as is compatibility with system materials. We want to have as little disruption as we can when implementing a new refrigerant. And so this is what I kind of was mentioning before: full stability inside the system and almost ultimate instability outside the system, right?
Sure. This is a great chart. This is very usable. When you start looking at why do we change refrigerants, Ty, why did we go to chlorofluorocarbon refrigerants in the first place back in the 1920s?
Oh, because they were not flammable.
Right. We were working with the exact same scenarios. We were looking at flammability, toxicity. Right? We were looking at what was the heat of compression, what was the performance of the compressor with the different refrigerants, what were the operating pressures. And so now we are another 100 years down the road going, hey, we're back at square one. And there's not a lot new. There's HFOs, which are a modified version of things that we already knew. But it's not like we have this whole soup kitchen of chemicals and we can go, surely one of these are going to work. We're struggling. Everyone is actually struggling to come up with a solution.
Yeah, there's actually... Oh, go ahead.
I'd like to see 717, how it compares to that chart.
Yeah, I mean, as far as the toxicity, you'd see it show up there. There's a flammability issue. It's a decent refrigerant performance-wise. I'll admit I haven't done a ton with it. Can't get too close, I guess.
Right.
But
it's not one
yeah, I mean, I didn't really. It's not really listed because of the proximity to humans. It's limited in application, from what I know.
Yeah,
but I won't speak too much there. Yeah, I mean, there's a really good paper on from ACS about the history of refrigerants that I like to refer to, and that talks exactly about why we went to chlorine and fluorine in the first place. And it is that low flammability and low toxicity. As you move on the periodic chart up and to the right, toxicity and flammability improve. So what's sitting at the upper right besides helium and inerts, it's fluorine, and right below it's chlorine. So that's those are our key elements. So 1234 ZE is close to a single molecule home run as we can. And actually, if you could flip back just for a second at the end of that list, I put an item in green that seems to be probably 90% of all the questions that we get these days is PFAS and TFA compliant. People want to know what is going on with PFAS, and we'll talk a little bit about that in a bit. But that's becoming another table stake that people are wanting in their refrigerant solutions, and the reason naturals are starting to become discussed and really looked at again.
Yeah, I do wonder if once we surpass GWP, we start focusing on TFA. Right. Because there's a lot of conversations on that, and we're trying to approach these professionally so that everyone has an understanding of what we're talking about.
Yeah. So ZE, we see this to enable no TFA and high performing blends.
What's TFA?
Trifluoroacetic acid. It's a decomposition component of some fluorinated refrigerants. So YF, as an example, degrades into 100% TFA. Which starts to become, as far as the single molecule performance parity and all the rest of it, it's great, but for the TFA question. So now we have to see, all right, well, if TFA becomes the next important thing, what's our play?
Right.
And we see it as ZE.
Okay. And we are starting to see ZE. Most people are not familiar with ZE at all, and it is a very interesting refrigerant, to say the least.
Yeah. So one of the reasons it's interesting is this TFA conversation. It's used a lot in chillers right now. I think that's probably where most people would know it. But just briefly, what's happening with EU PFAS and TFA. It's tough to keep track because of all the changes and things happening. But
Right.
basically, these 5 European countries, Germany, the Netherlands, Denmark, Norway, Sweden, proposed a restriction with a very, very broad definition in January of 23. Something about like 10,000 materials that we use every day. Many of these are
Common
probably,
chemicals.
essential in nature. Some of them, medical, pharmaceutical, all of those kind of use cases could be affected based on the broad definition as proposed. So what happened? Well, 5,600 comments came in from 4,400 companies blowing this back, saying, "Hold the phone. If you do this, it'll be catastrophic
Yeah.
to the socioeconomic
Oh, an
climate."
entire world of industries.
Right. I
Yeah.
mean, you could almost point to every industry would be affected by this in some way.
Yes.
So TFA, though, is a decomposition product of many refrigerants, and as I mentioned with YF, it's 100%. It is a major contributor to PFAS burden, and so it feels like what they're really after is TFA. It is present in nature, so I think there's still a question of whether or not it's truly bad,
Hmm.
but it's persistent. And so if the goal is to minimize persistence, that's the reason many are looking at it. And so, while they fight about, everyone decides what's the definition of a PFAS, and is TFA a PFAS, and why is it, do we want TFA or not? Industry's trying to respond to say, well, if they regulate it, what do we do?
Yeah.
And that's where we see ZE. So the decomposition into TFA, I have in that chart, there's 134A, which is about 20%. We have a blend 456A, which is basically just half. The composition is 134A, half the
Mhm.
composition, half the TFA decomp. There's YF at 100. And we have a blend R444A, which is 83% ZE. It degrades into 0% TFA. So the reason that we blend it is because of the performance. ZE gives up a lot in capacity, and we'll talk a little bit more about that when I get to some performance numbers. So we can blend it with things like 32, 152A, and even in the case of 456, 134A as an intermediate to match performance and reduce TFA.
Wow. So we are really starting to look ahead now. So now we're looking at what are all of our potential replacement refrigerants, and Koura's already manufacturing a variety of different replacement refrigerants in this process.
Yeah.
And it comes down to, what is going to be the requirements going forward from the industry and from legislations, from GWP restrictions, from technology transition rules. There are so many things that are all happening at one time. I don't think it's ever been as monumental in our history of our industry as it is right now.
And I think what we try to focus on the advocacy side is we understand the premise, global warming. Like that's where this starts, right? The stuff I started at the beginning, but are the regulations getting us closer or further away based on what we do in response to that outcome?
Good point. Yeah.
And so we'll talk LCCP after some time, but I wanted to at least show this chart really in support of blends.
Yes.
I think blends in stationary are well known and have been used for many years.
R410A.
Exactly.
It's a blend.
Yeah, and many others in ComRef and other segments.
Yeah.
In mobile, which is where I spent most of my career, they're less interesting, and there's just a lot more unknowns. But what they allow you to do is we're starting to see one molecule can't do everything anymore. So you need combinations based on how the criteria are changing. And if you open yourself up to understanding the benefits that blends can provide, what are the different materials, then all of a sudden the engineering gets less constrained, which is good news, right? You want the manufacturers and system designers to have options for one, competitive opportunities, but then also to address every new thing that we learn during a period of high innovation and high development. So this is a chiller study that we ran. We looked at NIST cycle D. The conditions are in the upper right. I won't go through all those, but it's basically the performance chart below it starts to compare the different refrigerants. So 134A was taken as a baseline. So as you look at the different blends, so 456A, that's the one I mentioned, it's about 50% 134A with R32 and then ZE. 444A is more than 3/4 ZE with some 32 and 152A. 513 is about a 50-50 split of 134A and YF, and then there's neat YF and neat ZE. We list 515B there as well, just due to the chiller applications. But I think you can flip to the next one where we zero in on the performance. We see the single molecule it has its, it has its own issues, specifically around capacity. So the green
Oh,
circle
okay, sure.
with 444A, all these are compared with 134A. So see the 100% at the lower left of the anticipated relative pressure drop, relative cooling, COP. That's our baseline for 134A. So if you look at 444A, you can improve both capacity and COP with a blend.
Okay.
And we see a little bit of a performance degradation in 513 and YF, but there's neat ZE. The COP looks good relative to 134A, but there's a huge capacity limit. So this really speaks to the fact that if TFA is our enemy, neat ZE is good, and a blend like 444A could be great.
Limited on it as a single constituent refrigerant.
Yeah, exactly. So if you can give up, a significant amount of capacity, sure, use the neat refrigerant. But if you blend it, you can kind of have your cake and eat it too, other than the fact that there's some temperature glide to a zeotropic blend and all the handling opportunities. But these are problems that we view are worth solving, right? We think, look, we're engineers, we're smart enough to do it. They're really capable people, and we as the manufacturers can give them options to say, is it a condenser redesign? Is it, how can we solve this problem? Not should we solve it?
Yeah, because if you look at those charts, I mean, what were our solutions? So if we go to like a straight ZE solution, we're going to have to increase capacity of the system then, wouldn't we? At least on the high side of our system. Larger components.
Which is cost, potentially, it's pressure drop, it's, what happens to the compressor performance, all of that. And the blends also let you say, all right, well, what's the incumbent? So we take that as like 456A. If you take a 134A system, 456A can drop directly in there with very, very minimal changes.
Oh, wow.
Same with 444A and 1234YF. I don't want to say transparent because there's some tweaking and optimizations that can be done, but it's generally same lubricants, same system architectures. It again lets you have cake and eat too when you consider it the blend.
Okay, and a reduced GWP over its original counterpart of like 134A here.
Yeah, for sure. I mean, those like 444A, the GWP there is less than 150. So we're already down, at that level. It's not one, so there's another trade-off.
Exactly.
That's the LCCP discussion that we'll get into shortly.
Okay. Wow. And Jason and Ty here, we thought 32 and 454B was going to be our common educational constituents. We knew there's a lot coming with commercial. Now we're having to look at, there's just a lot of science and a lot of research going into not just what is compatible as replacements, but what are the performance of these refrigerants going forward.
ZE is one of the interesting refrigerants from a flammability standpoint, as DOT and ASHRAE kind of consider them differently. Based on flammability testing. I want to say DOT calls ZE an A1 and ASHRAE calls it an A2L. So that one's in the middle. That one, that one has a lot of people scratching their heads.
Right. And that's why we have these conversations. And not just here on the show. We have our Did You Know the ESCO HVAC podcast. We just got to 54 countries with the podcast. And so the same kind of conversations. We talk about all of these important subjects, all these difficult topics, and we try to approach them professionally. And we make sure that we give you all of the resources that you need. So if you haven't joined in and checked out the podcast, we highly encourage you to do that as well. All right, so let's talk about some life cycle.
So GWP is becoming not the whole story anymore. If our goal isn't just reducing GWP, but decarbonization in support of a net zero, that's really the goal of all these regulations, then we need to consider LCCP. I've got a little bit of a tough slide.
That's all right. I'll get us over there.
Okay. So this was a study done for automotive applications. We're in the process of running more analyses in various segments, and we've got, I think, some software tools to do that. But in short, what does this mean? What are we talking about? It sums up the cradle to grave emissions. So the emissions forcing effects have three sources. Primary emissions, think GWP, the refrigerant breaking down. Secondary, so this is the balance of plant equipment that have emissions used for the equipment power, so think COP, and then the embodied emissions, what goes into making the raw materials. So if you think that GWP, is significant, you're right, it impacts the primary emissions. But as we continue to push on GWP, it becomes less and less of a driving force for LCCP, and the true summation of carbon emissions. So that's where efficiency and COP become a louder voice. And so what we see is for stationary systems, as GWP gets to at or below 300, GWP isn't the main driver anymore. It's COP. I attended a heat pump conference about a year ago, and that was the main topic. Was all they seemed to talk or care about was COP. How can I get more COP
Yep, energy
as
efficiency.
GWP comes down? And so that, I think it's responsible, right? I mean, you should never sacrifice efficiency and use GWP as kind of this one lever trick to do that. So if you look at the chart, it's a little bit maybe hard to see, but there's different US cities there. So Phoenix, Houston, Boston, Chicago, and on down. 134A is the red bar on the left. Our ZE-based 444A blend is in the middle, and then 1234YF is on the right. And so what you see is, despite the fact that 444A's GWP is about 90 versus YF's 1, the efficiency benefit somewhat or more washes out the emissions performance of that. So if you look at, let's see, so lower is better in terms of these numbers, right? So they're both always better than 134A as a baseline. But look at Houston, look at Phoenix, look at the high temperature areas. You see 444A performing better. There are a few where YF is better in, I guess, Montreal, Vancouver, some of the more cold climates. But I think in summary, you could see that it's really parity for a metric that is starting to become more and more important with our true goal of decarbonization.
Yeah, because that is a topic that I don't know that we've addressed very significantly here. It's one thing to be able to reduce our GWP, but when we start looking at compressor system performance, it is very significant for the refrigerant that we're using and the quantity of that refrigerant, because we have areas that need significant compressor work doing latent heat removal. And if we're not using the right refrigerant, we may be actually using more refrigerant than necessary because we're using a refrigerant that has a low performance at higher compression ratios.
Exactly. It washes out. So you're going to run the compressor harder, the discharge goes up, like all badness. So it's there's a lot of balancing factors, which is why it's important to develop these technical partnerships. I mean, we love having these conversations with our industry partners. A bunch of us are just kind of science geeks and like this kind of stuff, but it's, what are we really chasing and how do we get there? I think GWP isn't, if somebody says, well, GWP is 0, no one cares about that. Nobody at the at the climate council really cares. They care about net zero. And so this, looking at this view can get us closer to that outcome.
Wow. Okay. Any questions out there? Because I know I'm sitting here going through my mind going, I mean, I've been chasing GWP so long, I have to broaden my own scope of thought and realize that GWP is absolutely one of the components of the goal, but there are a variety of things happening all at the same time.
Yeah, it is a first step.
Yes.
It also governs the quota. So I don't want to sit here and say, well, don't worry about GWP once we get down, because even a GWP of anything 10, 20, that does impact the quota that we have available. So that I think that tie is still making GWP the most important one of these, but certainly one of, not the only factor.
Yeah, absolutely.
All right, here we go.
Okay, there's the drum roll. All right, so if we look at where we came from, where are we going?
Yeah. So how does this story end? I don't know if it ends or the next step. I mean, if you just told me you thought 454B was the end, I think that's more halftime at the moment. I mean, who knows if it's half of the first quarter, but I tried to list segments and where I see the development based on all these competing factors. So there's mobile, stationary, and chillers. So pre-AIM, the incumbent materials for each are listed there. So I've got 134A for mobile, 410A for stationary. I have 134A for chillers. There are commercial size that use 410A right now.
Right.
So in this intermediate phase, what we see is, what about for GWPs less than 750, which is about half of 134A. We've got 1234YF for mobile. That's great. Something like 90% of the cars out there are using YF. All good. What we have is a blend 456A for A1. It's an A1, so it drops right into 134A systems. The GWP is still 687, but to the point of how much of it can I use with my quota, you can use 2 kgs of that for every kg of 134A.
Exactly.
So what that does is extend the lifetime of some of these vehicles by letting you use more refrigerant longer because of the GWP being half. 454B and 32, I don't need to spend much time there. I think those are well known. 454B seems to be probably ahead, if anything, because of the significantly lower GWP there. But here come the A2Ls, right? That's the story of 2024. I think we were talking off camera about that. Like,
Yeah,
they're
this
on
is
the
the
way.
conversation every single day right now.
Yeah, critical. And then for chillers, we've got the 513A blend that's there, which is basically YF and 134A. We have neat CE, and then we have our 456A. So 456A is pretty close to 513A in terms of composition. It just swaps ZE for YF, basically. So then for 2029, that development window that I showed earlier, if we hurry up and get this validation and development done, what do we see? So for mobile, YF is still going to be there. We've introduced 444A, the ZE blend for, we've launched in the aftermarket right now for service, but it's a GWP 93 that drops right into YF systems, and it actually gives better performance. So higher efficiency, some of these numbers that we're after, higher capacity, it's a really good alternative for the aftermarket.
That's interesting.
CO2 and propane, as much as they continue to confused, and I don't understand why we would look at these. I get why we are having to look at them because of some of the pressures around it. So they're going to be there, and many companies are looking at them.
No, we've already seen CO2 744 systems being manufactured, particularly in Germany, for automotive air conditioning applications.
Yeah, another blend idea that that Koura's thought about too is, can you have a non-PFAS CO2 pressure level blend? So we've got a 485A blend that is completely non-PFAS. What is it? It's about 10 to 15% lower pressure. Still elevated. It's still up here, but lower than that high pressure, and it improves performance. It gets you more into that two-phase heat transfer zone, and it extends the call it the CO2 equator from how much of the country could use CO2 based on the high ambient performance.
Right. Yeah, absolutely.
But other stationary, I mean, there's active development happening right now. Nothing I can really share, but just a kind of a word to say, hey, the manufacturers are looking at this, and we are prioritizing development in the fluorine space with whatever happens with PFAS. Like, there will be we feel there'll be a place for fluorine there, in addition to 744 and 290. And for chillers, we continue to see neat CE and 444A as really good options in the future there. So that's sitting here today, what we see. But who knows, what will be around the corner that we haven't predicted yet.
Yeah, absolutely. One of the questions came in from Ray is, like when we start getting into medical lab equipment, that's probably not going to be using R290, and we're talking ultra low temperature scenarios, and we're probably going to be looking at things like ZE and like the 444s to work in those lower applications. But we are limited, when we look at the atmosphere that these types of equipment are manufactured in.
Yeah, and something I didn't list here. I mean, we have a product for minus 75 C ultra low temperature conditions. It gets down really low. It's CO2 based, but it's got 1132A and R23 and 125 in there. So it's a blend. So the GWP is still pretty high, but it's way lower, orders of magnitude lower than what the current incumbents are.
Yeah.
So that's a whole different discussion and segment. But again, there are options available that we're thinking about and bringing to market there too.
Yeah, absolutely. Lot going on. Oh my gosh. All right, Ty, Jason, you guys have anything you want to hop in here and ask Adam about? Anyone in the audience? There's still have a lot of people out there hanging around going, oh my gosh, more refrigerants. What do we do? Well, you hang in with us every week and you get firsthand information, not third, fourth, fifth, 10th. Uncle Joe's heard it through the grapevine. We want to make sure that you have.
I do have a question.
Ask questions. Yeah.
I have one. So in your blend, it's 444A. It uses a lot of ZE, you were saying. And we discussed that weird A1, A2L rating from DOT to ASHRAE on ZE. Does 444A, is that it's just straight 2L across the board, or does it carry that same weird designation?
That's a good question for DOT. I don't know the answer to that for DOT. I think for all practical purposes, A2L is the right way to think about that.
That's how I advise as well.
Yeah, but the DOT, I mean, I think they're being a little bit more discerning about that. I mean, because A2Ls are so, I'll call it barely flammable. I mean, it is worth pushing on, is it really? And could there be a system design where in practice it doesn't get to a flammable level? So we see that too. But I think we err on the side of caution, right? Take the more conservative path while we learn. So we're always, happy to answer questions, from specific folks using it about how it should be handled or where or how it's stored. But that'd be the guidance I would give. Let's err on the side of caution.
That's what I would say as well. Thank you.
Oh, here's a good one that came in. This is right up our alley. Thank you, Louis, for this one. So when do we expect the next lower GWP limit for residential to be set by the EPA, and what do you expect it to be? I have my thoughts. Let's hear everybody else's. Let's go through everyone's individual thoughts on what we anticipate to see as a residential solution beyond 32 and 454B.
Well, that's going to have to be legislatively done at this point.
I know.
And then
We're just assuming at the minute.
The AIM Act and the technology transition will both end up around 2035, 2036 in that neighborhood. So there would have to be legislation to move that, to kick it further down somewhere in that window, the 2029 window that he was talking about, if we're going to make any kind of transition whatsoever. So right now, your guess is as good as mine. The 150 was a good target. I think that's where a lot of folks are thinking, but there's nothing set in stone.
Yeah.
That's a question I get all the time. And I think the two prevailing opinions are, is it 300 or is it 150? I think with what New York's doing, I don't know if that's the question anymore prevailing. I think again, please don't hold me to this. This is my own personal opinion. It feels
Personal
like
opinions.
300 is starting to feel high to me, given everything, right? So 150, I think, would be the upper end and potentially lower. Is it 20 at that point? But if I had to guess and place a bet, I would probably say 150. And when legislation will have to say, because of the, you're starting to see these regulations work their way through the market now, and inventories and all of the supply chain issues are starting to really become affected and disrupted by this. Pricing is going to start to become more volatile of these incumbents because of availability. So
Absolutely.
How will everyone respond to that is the question, and we can't really predict that. So
yep. Nope,
the other question there becomes if we stay on GWP 20 or do we stick with the GWP 100, which could really upend things.
But you can imagine my thoughts on that. I mean, I think just a word. I think the reason that it's in question, and New York is pushing this, right? That's where we hear that, because the refrigerants degrade so quickly. Is 100 years the right time scale? Well, I think it isn't the refrigerants that you should look at. It's CO2. CO2 lasts in the atmosphere a heck of a long time. And so I think it's a more accurate reflection of the baseline comparison than it is the refrigerant. So we view that as another over constraint that we're under, an unneeded handicap that we would hold ourselves to.
I would agree with you on both of those. I think, again, personal opinion, I think 150 will be the target. And I do think, as you said, that if we're using CO2 as a baseline, then the GWP 20 isn't really cognizant of that lifespan of CO2 itself in the atmosphere. So,
right.
Ty?
Well, I love understanding the hows and the whys and all the other stuff that comes into it, but my perspective is different. Change is always going to happen, and give me a temperature and pressure chart, and it really doesn't matter what refrigerant we're working with.
Good call.
Superheat, subcooling. The engineers do all the testing on evaporator coils. I got to have the right airflow. The engineers do all the testing and how much refrigerant it needs. I follow that specification. And when it comes to the customers upset about the price, I say, hey, this is the change that's happening, and this is the price. And it really just simplifies that a whole lot more. I do love learning about all this, don't get me wrong. But when it comes down to what should we have, what we're going to guess about, it's too much for me to worry about. I love having the engineers, that do all this other work and testing for me. I just got to follow the directions they put in front of me.
You just got to know that by the time that system gets in your hands, how many people have gone through it, how many people have tested it, designed it. You folks put a lot of research and development into the refrigerants. They're tested to the nth degree before they finally get into the supply house. There's been so much that it has gone through. By the time I get it, the only thing, like you said, I need to worry about is, all right, I got to braze this in. I got to pull a vacuum. I'm going to try. Superheat is superheat and subcooling is subcooling. The refrigeration cycle doesn't change just because the refrigerant is flammable.
And to the point of price, I think, is you constrain, how much of it there is. I think the baseline price of 134A historically is not a fair comparison either. So you say, all right, well, why is YF so much more expensive? Well, it's more expensive than what 134A is today. But once we have other competitive options to it, like 444A, what's going to happen is 134A supply is constrained to that price. It's going to go up. So nothing will stay the same, even the baseline comparison. So I think it's important to recognize that when, looking at financials.
Yeah, absolutely. Howard Weiss has said it many a times. Doesn't matter what refrigerant we go to, it's still a refrigerant in a refrigeration cycle. And that's the important thing. And that's what we're here for. We're here to remove these stigmas, to help you have an understanding of what's coming. I do believe myself we're going to see a 150 as our next goal. I think we're going to see a variety of different applications of our low GWP refrigerants coming faster than people anticipated. And that's okay. And that's why we do this. That's why we get together every week to talk about these important things. So I encourage you to learn more, reach out to Adam and to Koura and learn about what's happening in this sector. We'll make sure to get that information out here. I got the QR code for you to, if you scan, that'll take you right over to their site, but you can also contact them through Adam as well. Let me get back to the very first card on that one in case anyone has any questions for Adam going forward. And that is about a wrap for today. Adam, you got anything you'd like to end with before we hop out of here?
Yeah, I just think there's been a lot of questions and discussion. We talked about patents and or is this just a play to try to get high price refrigerants? I mean, I think we see the constraints that continue to come up, and the constraints are there to solve real problems. And so what I could offer is that the manufacturers take this very seriously. We're passionate about this. Hopefully you hear that coming through and when I talk. But we view our role as a technical industry partner. So if there are these questions, if there are discussions, I mean, I come and talk to groups within companies sometimes to help share the story about a specific use case. So, I mean, more discussion, more collaboration is better. So yeah, just couldn't encourage that enough. If there's a question, ask it. If we don't know, we'll certainly find it out, because it's important that everybody gets on the same page here.
Yeah, absolutely.
I can tell you I've been doing a lot of training, a lot of speaking, a lot of sitting in groups and committees and things. And I actually picked up a few things in this presentation. This was a really good presentation. There's some things that I might want to incorporate. Yes, it was really beneficial.
Terrific.
Yeah, Adam and I first started talking about this. I was like, "You're the guy."
Well, I'm glad it was helpful. That spider chart was my favorite part, if I had to say.
Well, it is.
That's a great visual.
I like it. Yeah. We're visual learners, aren't we?
Yes, we are. All right. Well, if that is it, I think we'll call it a wrap for the day. Gentlemen, I appreciate all of you so much. And if anyone wants to connect with Adam, they can hop on LinkedIn. That's Adam Kimmel, and Koura, Koura. And everyone, we really appreciate you joining us this week on Did You Know, the ESCO HVAC show. Hang in with us as we keep talking about these transitions. We're actually going to have some equipment manufacturers on in the next few weeks talking about what their equipment looks like as they make refrigerant transitions. And we're going to do our best to have the very top educators from our industry every single week for your disposal. So Adam, Koura, thank you all so much. Everyone have a wonderful week, and I'm going to hop out of here and go enjoy Branson, Missouri a little bit, and I'll be back at it next week.
Hope you do. Thanks so much. This was great.
Everyone, thank you, Adam. I consider myself educated. Thank you.
Good deal. Right. All right, take care.
So we'll see you all next week on Did You Know, the ESCO HVAC show. Bye, everybody.